Welcome. Let me remind you that in the last class we had started discussing the expanding universe, and I told you that it is convenient to go into a coordinate system which is expanding with the galaxies, which is fixed to the galaxies, and this is called the comoving coordinate system. So, this coordinate system x is fixed to the galaxies. The galaxies are all moving away from one another. So, that is there in the scale factor a of t, which is an increasing function of time, and the physical coordinate r between two galaxies then, which keeps on increasing as a function of time. So, with this with these definitions, the Hubble parameter was the time derivative of the scale factor divided by the scale factor itself, and the present value of the Hubble parameter is then a dot by a at t equal to t0. T0 refers to the present time. Given this, so given the scale factor and the comoving coordinate system, we first considered a very simple model where the universe is freely expanding. There are no forces acting on between the galaxies, and in this model we worked out the behavior of the scale factor as a function of time. So, we found that the scale factor increases linearly with time, and at a certain time instant the scale factor reaches 0, and we chose the there were different constants of integration that come about when you write down a of t, and we chose the constant of integration suitably so that the time origin for time is at the instant when the scale factor becomes 0. The scale factor becoming 0 is a singularity which is referred to as the Big Bang. The entire universe collapses to a point. So, the time is measured from that event, and the age of the universe then, or the cosmic time, is given by t. And in this model we saw that the age of the universe at any instant of time is related to the inverse of the Hubble parameter at the same instant. So, the present age is 1 by h naught. 1 by h naught is referred to as the Hubble time, and in the last class I had asked you to estimate this in years. So, I hope we have done this. I have given the value over here. So, so if you assume that h naught is 100 h kilometers per second per megaparsec, the Hubble time comes out to be 9.78 into 10 to the power 9 h inverse years. So, the order of magnitude of the age of the universe, whatever cosmological model you use, is of the order of tens of billions of years, billions, right. This is approximately 10 billion years. So, it is of that order. Now, I also told you that this only gives you an order of magnitude estimate, because here we have ignored the influence of gravity, which will slow down the expansion of the universe, and the relation between the Hubble parameter and the age will be modified. We next put in the effect of gravity, and if you include the effect of gravity, you then have two equations which are written over here, two equations for the scale factor. The first equation tells you the second derivative of the scale factor is minus 4/3 pi g rho a. The physics of this is essentially that the motion of the galaxy over here, this is the observer who is observing this particular galaxy, the motion of this galaxy, the forces acting on this galaxy are due to the mass enclosed within a sphere encircling that galaxy, that is all. So, starting from this you can arrive at this relation for the scale factor. In addition to this, you also have the fact that rho into a cube is a constant. This is the conservation of mass. As the universe expands, the length scale increases proportional to a, the total mass in a volume has to, in some region, has to be conserved. So, that volume, the volume of that region increases as a cube. So, the density has to fall as 1 by a cube because the mass has to be conserved. Further, so this is also equal to rho naught the present density into the scale factor at present cubed. Further, we assumed that the scale factor at present has a value 1. We are free to choose whatever value we wish for the scale factor at present. So, we have chosen this to be 1. So, at present the co-moving coordinate system and the physical coordinate system are exactly same. In the past the co-moving coordinates would be different, okay, from the physical coordinates, or in the future also. So, these were the two equations that we had to solve, and we proceeded by integrating, by multiplying the equation with a dot time derivative of the scale factor on both sides, and then we obtained this equation a dot half a dot square plus 4/3 pi g rho into a 1 by a plus is equal to E plus E, okay, this is equal to this plus E. E is a constant of integration that comes about when you integrate this equation once. So, this equation is the first integral of this equation, and we interpreted this equation as follows. This term could be identified with the kinetic energy of this galaxy. This term could be identified with the potential energy of this galaxy, gravitational potential energy due to all the mass inside, minus g m by r essentially is this term. And then we know that in Newtonian mechanics, if I have a system like this, then the total energy of this particle is going to be conserved, okay. So, this is the total energy, which is a constant of integration, a conserved quantity for this motion. So, this equation could be written as T plus V, the kinetic energy plus the potential energy is equal to the energy of that galaxy. Remember, this is a purely Newtonian interpretation, okay. Now, so this is the equation that we had, and before proceeding further, let me point out one fact. The fact is that the motion of this galaxy is exactly the same as the motion of a particle thrown radially outwards from the surface of the earth, because a particle thrown out radially outward from the surface of the earth will be governed, the motion of that particle will be governed by exactly the same equation. Now, for a particle which is ejected, a projectile ejected radially outward from the surface of the earth, the mass that is inside the earth remains fixed, the mass that contributes to the gravitational acceleration. Similarly, for this galaxy, the mass that contributes to the gravitational acceleration remains fixed, because the matter inside this is never going to overtake this galaxy. According to Hubble's law, the matter inside this sphere is moving slower than the galaxy, because it is at a smaller distance. So, this mass is the mass inside this sphere will never overtake this galaxy and go out. So, this m is basically a constant independent of time. So, this equation is essentially the equation of a projectile which is being projected outwards from the surface of the earth, and we very well know what the solutions are, okay. The solutions are determined by the value of the total energy of the particle. If you have a total energy which is negative, then if the particle has an energy which the particle which is being ejected out which is the projectile has a negative energy, then what happens is that the particle will go up to a certain distance, and then where the kinetic energy becomes 0, and then it will fall back again. If the total energy is exactly equal to 0, that is the situation where this particle has the escape velocity, and we have just imparted the escape velocity to this particle, right. So, it will reach infinity, true, but when it reaches infinity it will be at rest, it will come to rest at infinity, okay. And the third possibility is that the particle has positive energy. In such a situation, the particle will reach infinity and have a non-zero velocity. So, these are exactly the same things will happen here also, depending on the value of E. So, it is quite clear that the evolution of the scale factor is crucially dependent on the value of E. Okay. Then I address the question, how can we determine the value of E, at least in principle. So, to address that question, what we did was we wrote the same equation in a slightly different form. We replaced rho naught here with the density into A cube, and we then obtained this equation, which is essentially this. And if you take this equation and write it at present, then you have this relation between the constant E, the energy E, and the H naught square, and this ratio over here, the dimensionless ratio over here. So, we see that in this dimensionless ratio we have the present density of the universe in the numerator. In the denominator we have a density, something of the dimension of density, which is determined by the value of the Hubble parameter. This density is called the critical density, and the present value of the critical density is 3 H naught square by 8 pi g, and the ratio of the actual density to the critical density of the universe we call the density parameter. It is this ratio which determines the value of E. Further, I also told you that this ratio, that the critical velocity, critical density is a very general definition. It is not only that you can define it at present, you can define this at any epoch. So, it is 3 h square by 8 pi g at the epoch in question, and the omega density parameter also can be defined at any epoch. It is the ratio of the two densities at that epoch. I had also asked you to estimate the value of the critical density. So, I hope you have done this. If you put in the value of the Hubble parameter and the other constants, it comes out to be, so the value of the critical density comes out to be 1.88 into 10 to the power minus 26 h square. The h square is there because we have parameterized the Hubble parameter in terms of this h, kg per meter cube. So, what does this tell us? This tells us, or okay, before that you can also write this in units which are sometimes more convenient in astrophysics. You can write it in terms of solar masses per megaparsec cube, and it then turns out to be 2.78 10 to the power 11 solar masses h square solar masses per megaparsec cube. What is the significance of this density? And the significance of this density is that if the actual density of the universe, if the actual density of the universe at present is more than this value, then the density parameter is more than 1 and the value of the energy is negative. Okay. If the actual density is just equal to this critical density, then the omega density parameter has value 1 and the value of this energy is 0. This corresponds to the particle that is being ejected having just the escape velocity. If the density of the actual density of the universe is less than the critical density, then the density parameter is less than 1 and E turns out to be, the energy turns out to be positive. So, all of this is summarized and it is summarized over here. So, if the density parameter is 1, the energy is 0. So, the density parameter being 1 essentially corresponds to a situation where the kinetic energy of this particle exactly balances the potential energy of the matter of the due to the mass inside. That is the density parameter 1. Whereas if the density parameter is more than 1, so the density is more, so the potential energy is more than the kinetic energy. Whereas if the density parameter is less than 1, the density is less, so the potential energy is less than the kinetic energy. The situation that we have already considered, which is free expansion, essentially corresponds to putting the density parameter to 0, because in that model there is no gravitational force, and if you have no mass, no density in the universe, no matter in the universe, so my galaxies are just test particles, they do not exert any gravitational force, then I will recover the free expansion model, which essentially corresponds to omega naught equal to 0. Okay, so that is the case where the constant is h naught square by 2, free expansion, which we have already worked out. So the main thing then is that if you can determine the actual density, the Hubble parameter I have told you is quite well determined, we shall discuss later how it is determined. If you can determine the actual density of the universe, you can then determine this constant of integration E, and you can determine then you can work out the solution to this equation, and you know the complete evolution of the universe. Okay. Let us first, before we discuss this any further, let us first work out the solution to this equation. What does it look like? So let us first take up one situation which is the simplest, where the value of this energy is 0, which is the critical model. Okay, let us just work out the value of the scale factor. What does it look like? So the scale factor corresponding to omega naught equal to 1, this is the critical model, this is the critical universe, it is also called the Einstein de Sitter universe. Einstein de Sitter model, okay, or universe, or just the de Sitter universe. Also the critical cosmological model. It is critical because it is just the dividing, it is the dividing line between the two models, one with positive value of E and the other with negative value of E, for which the behavior are quite different, completely different. So for this particular model, let us work out what the solution is, and here the equation is rather simple. So we can start off with this equation. Rather it is more convenient to work with this. So let us start off with this equation, put E equal to 0. So we want to integrate this equation with E equal to 0. So the equation, so what you do is you just take the square root of the right hand side, multiplied by 2 and take square root of the right hand side. So what you have is dA dt is equal to 8 by 3 pi g rho naught to the power half, and you have a to the power minus half over here. So this is a very simple equation to solve. What all that you have to do is you have to take this onto the right hand side and integrate this. So what we have is that dA into square root of a is equal to some constant, let us give it a name, I will just call it C into T. I have just put this over here in this constant, and there can be a constant of integration here, but we would like the scale factor to be 0 into dt, sorry, that is the thing that we have. So let us integrate this equation. If I integrate this equation, what we will get is a to the power 3 by 2 is equal to, so if I have a to the power 3 by 2 here, I will have 2/3, so I can take it onto the right hand side, and what I will get is 3 by 2 into this constant into t plus another constant of integration, which I will set equal to 0, because I would like the scale factor to vanish when t equal to 0, not at some other instant of time. Okay. So we can then write down the scale factor a as a function of time is equal to how much is it equal to, so we have 3 by 2 over here, and if I take 3 by 2 inside the square root sign, then I will have 3 will cancel out and I will have a 3 left, because I have to take square of this, so I will have 9 3 on top, and if I take this inside I will have a factor of 4, so I will have 6 pi g rho naught to the power of, so here I have to the power 3 by 2, here I have to the power half, so I will have to the power 1/3 t to the power 2/3. So that is my solution in the situation where omega naught is equal to 1, the density parameter is 1. The crucial point here is that the scale factor is proportional to t to the power 2/3. The constant is some number which is there. Okay, that basically determines the normalization of A. We would like A to be 1 at present. Okay. So let us for this model now determine the value of the Hubble parameter. So the scale factor is something that is not physically measurable here. The quantity that is measurable is the Hubble parameter. So let us determine the value of the Hubble parameter in this model, right. So how does the Hubble parameter evolve with time for this particular model? So in this model, if you calculate the Hubble parameter, A dot by A, so if I differentiate this, I will have the constant 2/3 t to the power minus 1/3. So let me write it here, 2/3 the constant t to the power minus 1/3, that is the A dot divided by the same constant t to the power 2/3. So now you see that the Hubble parameter h of t in this model comes out to be 2/3 into 1 by time. Or at any instant of time the age of the universe, so let us say the present age is equal to 2/3 of the Hubble time. So the present age of the universe, sorry, at that instant, not the at that instant of time, and the present age of the universe is 2/3 the present value of the Hubble parameter. So what do we see? We see that the as far as the Hubble constant is concerned, the main consequence is that the gravitational slowing down due to gravity will essentially reduce the age of the universe. So, if I had no gravitational slowing down, then the age of the universe is exactly the Hubble parameter, whereas if I am living in a cosmological model where the density is exactly balancing the critical is exactly equal to the critical density, omega naught is 1, then the age of the universe is 2/3 of this value for the same value of the Hubble parameter. Okay, so the age is smaller. So we have worked out two cosmological models already. We have worked out the solutions for two cosmological models. Let me draw these solutions schematically. The first solution that we worked out, A as a function of time, the first solution that we have worked out, we have linear expansion of the universe. So, the universe expands like this, that is omega naught equal to 0, and then we worked out another model where omega naught is equal to 1, and we saw that it is proportional to the scale factor grows as t to the power 2/3, and we can draw the nature of the curve. So, let us draw the nature of the curve. The nature of the curve will look like this. This is omega naught equal to 1, and it will become flat as you approach infinity, because the slope of the curve A dot is 1 by t to the power 1/3, and as t goes to infinity that goes to 0. So, the slope will approach 0 as t goes to infinity. So, that is the omega naught equal to 1 model. Now, the question is, one has to now work out the other cosmological models corresponding to different values of E, but we know that the other values of E, we know the problem, and the solving this equation is rather straightforward for different values of E. It is not a very difficult thing. It may involve some amount of a lengthier calculation, that is all, but it is not a very difficult conceptually not a difficult calculation. It is essentially the same problem as that of a projectile thrown from the surface of the earth. It is exactly the same problem, projectile, which is already familiar to all of us hopefully. So, we know that if E is negative, or if omega naught is greater than 1, the particle will return back after some distance. So, the model will look like this. So, for omega naught greater than 1, the universe which is expanding will not continue to expand forever, it will reach a maximum value of the scale factor, and then it will collapse back. You will have what is often referred to as the big crunch. So, you have the big bang at the start, and the universe will end with what is called a big crunch. Okay. The third possibility, which the other possibility, is omega naught less than 1. For those cases, the slope will reach a finite value. We know that the particle has a finite velocity when it reaches infinity. So, the model will look something like this. It will have a finite slope at infinity. Okay, and here this is the extreme situation where omega naught is 0, which is from the start, right from the start it is a free particle. All of these models will approach a free particle at infinity. This will be a free particle at rest, this will be a free particle with a finite velocity, this is a free particle to start with. I will not work out the mathematical forms of these, you can look it up or work it out yourself, but this is the broad nature of the behavior of the scale factor. Now, let us, so you see the crucial point here is that the behavior of the universe, of the expansion of the universe, depends crucially on the value of the density parameter. So, it is essentially it is very essential to determine which cosmological model do we live in. which of these is our universe, that is the crucial question. We would like to know what is the evolution, what is the fate of our universe, what is the past evolution of our universe. After all, cosmology, we would like to study the whole universe, determine its past evolution, its future, etc. Okay, so this is determined by this density parameter, and density parameter I have told you is the ratio of the actual density to the critical density. So critical density is known. The main problem lies in determining the actual density of the universe. How to determine the actual density? So the difficulty lies over there. So the difficulty lies in determining rho naught, because if you know the density, you can straight away determine what the value of the density parameter is. The main difficulty lies over here in determining the density. Why? What is the difficulty? Let me briefly just try to give you an idea of what the difficulty is. What you can measure here directly from Earth, for example, is the light coming from different astronomical objects. So you can measure, what you can measure here is the luminosity. You can measure light, electromagnetic radiation. So you can measure the amount of light coming from different galaxies, for example, and you know the number of galaxies, number density of galaxies. So if you know the luminosity, so what you know is the luminosity of objects. This is what you can measure. You do not know what the mass, how to convert this into the mass, and you can determine how many objects there are, but question is what is the relation between the luminosity and the mass, how much mass does it correspond to. Now we have seen, for example, for stars the relation between luminosity and mass is not linear, it's a complicated relation, right. So this is one of the big uncertainties that you have, how to convert luminosity into mass. This is if you believe that all that you see is just the luminous matter, but the problem is much more severe than this, because we have already seen that there are components of the matter which are referred to as dark matter. What is dark matter? It is matter which emits no light, which we do not see. We know it is there because it exerts the gravitational attraction. If it exerts the gravitational attraction, it will contribute to this equation, it will contribute to the mass density inside, but we do not see it, it is dark, it does not emit radiation directly. For example, we discussed the rotation curves of galaxies, and I told you that there is evidence that you require dark matter to explain the flat rotation curve, and that is not the only situation where you need dark matter. So a large component of the density of the universe is believed to be dark, and we do not know what this dark matter is. So this is another problem that we have. Okay, so we do not know, there is no way of directly measuring the density. Okay, so this is something which cannot be directly measured, the density of the universe. So if you think that you could actually measure the density and determine the value of the density parameter, that is not feasible. Okay, so one has to adopt indirect means for determining the value of the density parameter, and that is the first thing that we have to realize. Discussion till now has entirely been based on the observations of galaxies and the idea that the entire universe is filled with galaxies and these galaxies are moving apart from one another. Let us now jump to a very remarkable discovery that was made in 1964, observational discovery in the year 1964. And there were quite before that there were speculations that one expects to discover such a thing. We shall learn about these later in this course. Okay, let me just jump straight away to the discovery. So at that time 1964 1960s, satellite communication through electromagnetic waves was being developed, and there were two radio astronomers, Arno Penzias and Robert Wilson, who were working at the AT&T Bell Laboratories in the USA, and they were using this radiometer. So this is a radiometer to study the noise for satellite communication through electromagnetic waves, and they were working at around centimeter wavelengths, somewhere over there. And so what they were doing was they were using this radiometer to characterize the noise from different directions in the sky. And you expect, for example, the sun to produce some electromagnetic radiation at those frequencies, at those wavelengths. The bulk of the radiation we have seen comes in the visible, but there will be some part of the spectrum which I have already told you in those wavelengths. In addition, there will be some radiation coming from our galaxy, but both of these things we know they rotate in the sky. The sky is the earth is rotating, so their position in the with respect to the vertically upward direction will keep on changing with time, and any such radiation you expect the contribution to vary with time. But Penzias and Wilson found that in addition to all of this, there was some component, some radiation which was coming quite uniformly from all directions in the sky. So this was a radiation which was coming from all directions. So if you have a radiometer and point it, they found that there is a component of radiation which is more or less the same from all directions. The radiation was, so they could not identify this radiation with any known astronomical or terrestrial source, and Penzias and Wilson were worried about this radiation. They were very sure that this radiation was not generated inside the radiometer, it was from outside, and they could not identify any source for this. At the same time, there was a group of theoreticians and observationalists at Princeton University who were trying to detect such a radiation which was coming from all directions, which had roughly the same intensity as the radiation that was discovered by Penzias and Wilson. So when they heard of Penzias and Wilson's discovery, they immediately realized that the radiation that Penzias and Wilson had discovered is actually cosmological in nature, it is cosmological. So that is why it is referred to here as cosmic noise. So the radiation that Penzias and Wilson discovered is not only is the radiation isotropic around us, it is, so the radiation comes, the amount of radiation coming is the same from all directions. Not only that, but we believe that the radiation is also homogeneous, it fills the entire universe. So this radiation fills the entire universe, and this cosmological radiation was expected to have a, so it is expected to have a black body spectrum. Planckian spectrum. So black body Planckian spectrum. Okay. So remember that this black body Planckian spectrum arises when radiation is in thermal equilibrium with matter, and they expected this radiation to have a Planckian spectrum if it is cosmological in origin, a black body spectrum, and its temperature, a black body radiation is completely characterized by a temperature, was expected was around a few Kelvin. Now obviously Penzias and Wilson made the observation only at a particular wavelength or frequency, and they could not determine the spectrum. The fact that it was a black body spectrum could not be determined by them. So you required observations at other wavelengths to establish the fact that this is a black body spectrum. It is now quite well established and well accepted that the radiation that was originally discovered by Penzias and Wilson is indeed a black body spectrum. There was a satellite, the Kobe, the NASA satellite called Kobe, Cosmic Background Explorer, which had an instrument called FIRAS, Far Infrared Spectrometer, which measured the spectrum of this background radiation. So this background radiation is called the cosmic, because it is cosmological, it fills the entire universe. Microwave, because this is in the microwave part of the spectrum, it peaks in the microwave part of the spectrum. Background radiation, CMBR. So this is a radiation that fills the entire universe. It has a temperature, the temperature as measured by Kobe FIRAS is 2.73 Kelvin. And the fit to a black body spectrum is so good and the measurements were so precise that the error bars, you can see some error bars here, these error bars have been, so the data points are shown over here, the data points, and the smooth curve is a fit. So is actually a black body spectrum, not a fit, it is a black body, the best fitting black body spectrum, which corresponds to a Planckian at 2.73 Kelvin. The errors on these data point have been magnified, the 1 sigma errors have been magnified 100 times so that you can see them. They are actually 100 times smaller, they have been magnified 100 times so that you can make them out in the graph. The measurements were so precise, and this is the most accurate black body spectrum that has ever been measured, even on Earth. Okay, most precise measurement of a black body spectrum. So, and both, so these are very pathfinding works in cosmology. So both Penzias and Wilson, they received the Nobel Prize for this discovery, and John Mather, who was the leader of the team that measured the spectrum, also received the Nobel Prize quite recently in 2006 if I am correct. Okay. This satellite, this Kobe satellite was launched in 1990, the measurement was made in 1990. Okay, so this black body, so before that there were points, there were discrete points which had been measured, but there was still scope for deviations from a black body spectrum. It is now well established that over this entire region the spectrum is black body, it is a Planckian spectrum. Okay, and notice that the peak occurs at around 2 millimeters. Okay, that is where the peak of this spectrum occurs, around 2 millimeters, and here you have the frequency in units of centimeter inverse. Okay, so it is 5. Okay, so this is the cosmic microwave background radiation. So for the time being, we know, at least we know that there is one more component in addition to galaxy, and that component is a black body radiation. So we have to also take into account the black body radiation in our discussion. We shall study, we shall come back to the cosmic microwave background radiation in more detail in later lectures. Okay, for the time being, let us just study its effect, one aspect of this radiation. So the cosmic microwave background radiation has a temperature T, so it is a black body radiation with temperature T, and you know that if there is a black body radiation with temperature T, then it has an energy density which is T into the Stephen Boltzmann constant AB T to the power 4. This is the energy density epsilon or U, let us call it U, corresponding to this black body radiation. And I will request you to calculate the energy density corresponding to this. Okay, calculate the energy density corresponding to this 2.73 Kelvin. Not only do you have an energy density, you can also think of a mass density, equivalent mass density. If I divide this by c square, rho. Okay. And so there will be a component of, so let us call this rho gamma, that is a component in the CMBR, and this will give us the value of the rho gamma at present. Okay, if I take the present temperature of the CMBR T naught, U naught. Okay. So not only should you calculate the energy density, but you should also calculate the ratio of the density in the CMBR to the present value of the critical density. So this is the density parameter omega gamma naught or omega CMBR if you wish. So this is the contribution from the cosmic microwave background radiation to the density of the universe. Okay. Now the question that we are interested in is what happens to the density of this component of the universe as the universe expands. For galaxies and other such matter, we have seen that the density into a cube is a constant. So as the universe expands, the density falls as a cube. Let us see what happens to this. Okay. So the expansion of the universe, let us look at a finite volume of the universe. Let us say it is a unit co-moving volume. So the volume is scale factor A basically, that is the volume A cube. So the volume of this is A cube, it is unit co-moving distance, volume of unit co-moving distance. Okay. Now we are assuming that the universe is undergoing adiabatic expansion. So this is like a volume which is undergoing adiabatic expansion. So this is an assumption which is quite well justified. This, so a volume, any process may be assumed to be adiabatic if it does not exchange heat with the surrounding, right, and it is quite a reasonable assumption that in the expansion of the universe, one part of the universe does not exchange heat with any other part of the universe. Okay, so we are going to assume that the expansion is adiabatic. So if I take this volume and consider adiabatic expansion, then we know that it has to satisfy the first law of thermodynamics. Which is that the pressure into P dV plus the change in the internal energy we know is the internal energy per unit volume into the volume, this should be equal to 0. So we are going to use this to determine how the density of the cosmic microwave background, the energy density of the cosmic microwave background radiation changes as the universe expands. Let me bring today's lecture to a close over here and take up this for discussion in the next lecture. Okay, so we will immediately start the next lecture.